Welcome to the lectures on DC motor testings. So, last time we learned about the Swinburne test, which is one of the simplest tests, but at the same time it does not tell you many things. I mean, you will never be able to predict really how machine, when carrying the rated current, will behave. Those things are not there in the Swinburne test. You estimate the rotational loss, and on pen and paper you go on predicting what will be the efficiency, how much torque will be produced, this that. But another way of testing that looks like by direct load the machine. But as I told you, loading a machine by connecting the mechanical load of a large machine, say 50 kilowatt DC machine, 50 kilowatt load is very difficult to obtain. In any case, what is done is this, that is called brake test. See, DC brake test, direct loading. Sorry. This method is called direct loading. The second method is direct loading. What is done, or it is also called DC, by using braking, mechanical braking, we will do the test. Let us see the arrangement. Arrangement is simple. Suppose this is the motor, this is the motor. Okay. This is the motor, this is the shaft of the motor, shaft. Okay. Now, on the shaft of the motor, another drum type thing is connected on the shaft of the motor, it is coupled. And here, so this is called pulley sort of thing. Okay. And what will happen is this, I will just tell you the arrangement. So, from the end, if you see this end, it will be like this, that will be easier. This is the shaft of the machine, shaft. Now, here there is a grouped pulley is connected. Okay. A cylindrical thing is inserted and firmly connected here. Now, and the machine shaft is like this, so motor is there. So, this is the shaft of the motor, shaft. And what you do is this, now you connect a belt. This is the belt which will go through the groove of this pulley. Okay. This bit. And there will be and these sides are connected, you can adjust you can move it like this, so that the tension in this pulleys can be adjusted. For example, there will be some like your nut and bolt arrangement. So, you can move this either this direction or that direction. It may so happen that the tensions, so that it will develop tension in the strings. It may so happen that what I mean to say, that this is the pulley drum, this is the drum or drum you call it, and this is the shaft of the machine. Shaft of the machine is this, and these two are very loosened, these screws are loosened. Then how it will, and it is on a stationary structure, it is fixed here. So, this belt will then hang like this, it will it may so happen if the tensions on the strings are loosened, it will be like this. It is not touching this one. Now, adjusting the tension here, you can push it up, and so that it comes into the groove, and which is connected to the shaft. Got the point? And there will be an indicator like a weighing machine, mechanical weighing machine, which will give you the tension you have applied to this two sides of this string belt. This is belt. Therefore, if these tensions are not there, it will just slack like this, and if the motor is running, it is running under no load, is it? If the motor is, so the pulleys are here in this diagram. If I want to show, this is the belt here, it will go like this, and on the top it is connected to, these are stationary. So, you can adjust the tension of the strings. Now, what you do, it was loosened very much, the tensions, you tight them, so that it will fit in there in the groove, and then suppose this will give you the force applied here, how much, and this is force applied there, how much force. Therefore, the difference of these two will give you the torque produced, torque you have applied to this rotating thing is F, if this is suppose radius of the pulley, F1 minus F2 into R. So, this is the mechanical opposing torque you will apply on the shaft of the machine. So, you are directly mechanically loading it. The moment this is very, it will go inside the groove with F1 and F2, and you have applied an opposing torque. If F1 is greater than F2, the torque you will apply like this, and machine must be rotating in this direction, then only it will be loaded. Clear? So, this is the load torque present on the shaft of the machine. And suppose the machine is running at a high speed 1000 rpm, and you have loaded the machine. So, this will give you the net mechanical torque on the machine. Where that power will go? It will only hit this pulley and the belt, this junction. It will not going to do any mechanical work. The same power is to be drawn from the supply for this machine, and that power, majority of the power will be dissipated on the shaft, it will become very hot. So, it is called direct loading method. So, you calculate this is the load torque, multiply the load torque with 2 pi n, n is in RPS, you will get the mechanical power output, and here you measure what is the input power. The moment you load the machine directly, you will see armature current, ammeter reading is increasing, and therefore, you can calculate the efficiency of the machine directly. This output power will be how much? The difference of the tension into what is this R? No resistance, it is the radius of the pulley, effective radius, into 2 pi n omega in RPS. This is the output power and your input power is V into IL. Got the point? So, this is called direct meshing, and this time armature will carry the rated current. It will draw whatever power it delivers to the so called load here, which is dissipated as heat, simply as heat. That power of course is to be drawn. Apart along with that power, of course, the other losses will be the input power. So, it is not a very efficient method of doing this, just directly loading the machine, but there are a couple of small problems you will be able to solve it. So, what I do here, on the shaft we connect directly the load, at least I mimic the load. It is not running a pump and raising water. In the laboratory I cannot do that, but laboratory arrangement I can do this, knowing fully well all the powers will be wasted here. This you cannot touch. After doing this experiment, it will become too hot, this pulley inside groove and the belt. As a friction heat power, it will be lost. But nonetheless, it will give you idea. You can see whether in the commutator segment from the end view of the machine, whether it is doing perfectly okay. Armature resistance at high current will be higher, is not. So, the efficiency that you estimate will be better, and also you can see the performance of the machine visually. Okay, there is no problem so far as commutation goes, no flashover, very large flashover taking place. Those things were never possible in case of Swinburne test. That was the problem. So, it is by direct loading you can do this, solve couple of problems, that will be the thing. But certainly for large machines, this way of testing the motor not good, you are wasting all the powers just like that. Although physically the armature will carry the rated current. It is like asking that a 100 kilowatt transformer test it directly in the lab. Okay, that power will be wasted. So, in case of transformer, for example, there was a better method. Instead, I will pass the direct current. You can see in case of transformer, do no load and load test. From that you can predict efficiency. Once again, the drawback of that method is actual temperature rise of the machine will not be understood by that test. And also all the only little power is drawn, that was the advantage of that method. Similarly, in case of DC motor, when you do no load test only, Swinburne test, that is fine, very good, only little power it will draw, and from that you predict the efficiency or want to see the performance of the machine physically. But the second objective will not be met, because it is after all armature, you are not allowing the rated current to pass. So, the direct loading method is this, where actual real current will flow in the armature, direct loading you do, but disadvantage is all the powers will be wasted. So, there is another better method, and that is called Hopkinson's method, Hopkinson test. Very interesting method. It is equivalent to Sumpner test in a transformer. Okay. What you do is this, in Hopkinson test, as it will unfold, you will see that machine will carry rated current, armature currents will be rated, I will be able to pass. But the power drawn from the supply will be very little. That is the whole idea. But the condition for carrying out this test is that you require two machines. You cannot do on a single machine this test. Two similar machines, similar DC machines, this is a shunt machines, are needed. Similar means its rating, voltage rating, current rating, kilowatt rating, all these things. Now, what is the connection? Connection is this. This is one machine. It has got its field. Okay. And this is its armature. So, connect the first machine, machine 1, as a shunt motor. Okay, and give rated supply voltage. I have not drawn yet the second machine. So, apply rated voltage. So, it will run as a motor. So, this machine I will machine 1 I will run it as a motor. Acha, the second machine whose ratings are similar, identical sort of thing, it will have its armature, it will have its field, and I will insist that these two motors should be mechanically coupled. That I am showing it by this line, that is mechanically coupled. What does it mean? Mechanically coupled means their speed will be same. Acha. Now, what I will do is this. So, the second, this is the machine 2. Idea is very interesting. Machine 2 is this one. The field of this machine 2, I will connect it like this. Second machine separately excited, because supply is connected, its field will be present. And so this is the connection. Okay. And then I will follow the connection. This I will connect, and here I will connect a shorting switch and connect like this. Now, let us understand. Give supply here. This shorting switch is opened initially. Okay. This current is field current of the motor. It will draw, because V by RFM will give you this current. Similarly, this supply is there, therefore, this current will be the generator field current IFG. Fields are excited all the time. Now, I have given supply to this machine, its armature and field are energized. So, this motor is going to run at some speed n. Similarly, the generator speed cannot change, because it is mechanically coupled, it will also run at that speed, and that will be the thing. Now, look at the second machine. Second machine, this field current is there and it is running at some speed. Therefore, there will be induced voltage across its armature k phi n, its phi is there, n is there. Therefore, there will be induced voltage between these 2 points. Now, if I connect a voltmeter across this shorting switch, what do you think this voltmeter reading will be? You should be careful. See, if you look at the armature circuit, if you allow me to remove this, it is coupled, I know that, mechanically coupled. Here inside this machine, what is the equivalent circuit? There is some RAM and back EMF of the motor, EM. And what is the equivalent circuit here? RAG and the generated EMF. Now, this generated EMF, this I am drawing here, RAG, it could be this way, EG, or it could be, you do not know na, when you are starting this experiment. Is not. Therefore, the reading of the voltmeter depends upon whether generator has developed a voltage such that the upper side is plus, lower side is minus. Or lower side is plus, upper side is minus. Either of these these two will happen here. Therefore, reading of the voltmeter will be either EM plus EG or EM minus EG. So, if it is EM plus EG, that voltage will be very large and I should never operate this switch. If I find this reading of this voltmeter is about twice this supply voltage, EM will be close to V, twice V of that order, then better stop the machine, either interchange the field terminal so that the supply polarity becomes like this. This must be ensured. This is EG. For doing this test, this must be the polarity of the induced voltages in the motor, that is the back EMF here, and this is the generated voltage of the generator. So, under these circumstances, reading of the voltmeter, reading of voltmeter will be the difference between these two, EM minus EG. This will be the difference. So, up to this point, supply voltage, this is running as a motor, the switch is open, the field of the generator is also excited because it is drawing a current. So, it will develop a voltage. I should ensure the polarity of this voltage is same as this one and S is opened, and then this voltmeter reading is difference of these two. What you first do is this, try to make this voltmeter reading close to 0. How can I do that? I will adjust the field current of the generator, this resistance I will adjust such that EG and EM are same and this will be close to 0. And if it is close to 0, then what I will do is this, I will close the switch. When this is true, then close S, so that you are sure there will be no circulating current. Okay. Now, so the final circuit after you have closed the switch, voltmeter reading will now become 0. So, it will now be like this. So, I will, so successfully you have what is called parallel them, and this voltmeter reading has no meaning now. So, it was connected earlier, but I am not showing that. So, this will be the thing. Acha. Therefore, now both the motors are mechanically coupled, their speed cannot be different, they are same, and it is steadily running as this one. Now, what is done? This, as I told you, is already running as a motor. Now, what this fellow is doing? Is it also running as a motor or a generator? What I will do is this, I will increase, suppose you imagine there is an ammeter connected here, ammeter connected here, DC meter with this side ammeter polarity is plus minus, MC meter, moving coil meter. I will, if I increase the field current, then Eg will become greater than Em and current will flow like this. It will try to drive current in this direction, provided if Eg is greater than Em. How it can be greater than? I will increase the field current of the generator. Greater than V, close to, because this armature resistance drop is neglected. What I am trying to tell, this will be greater than V, no doubt, but anyway that is close to Em, that part will be coming. So that it will circulate current like this, and this current I will call IAG. This will be the thing, clear. So now the situation will be that this machine will be running as a motor, this machine will run as a generator, because through the plus current is coming out, through the plus of this back EMF current is entering, and this is IAG, armature current of the generator, and this is the thing, that is both the machines are loaded. Now, let us see what is the implication, whether this armature currents, how it relates with these currents. What will happen is this, mind you, in this circuit, as was correctly pointed out, this voltage is same as V all the time. So, generated voltage V plus IAG RAG is EG. Similarly, V minus this IAM, if I call this current, is IAM, armature motor current. So, V minus IAM RAM is your back EMF, those things are prevailing like this. Acha, let this current be called the line current drawn from the supply. Mind you, there is only one supply, VIL. Acha, what is the total input power to this set? It is V into IL. The goal is to first estimate the rotational loss of the machine. So, what I will do is this, I will do rather quickly here, so that you can understand understand that it is not at all difficult. I will first not write, in the next lecture I will write, but first what I am telling is, what is this quantity? Power drawn from the supply. Acha, from this I will go on subtracting the losses. What is the field copper loss? V into IFM. VIL is the total current drawn by these whole two sets, subtract the copper loss of the field circuit of the motor, also subtract the copper loss of the field circuit of the generator, because this is also coming from the supply. So, V minus I f g, this is the thing. Then I will subtract the copper loss of the motor. How much it will be? I a m square into R a m, this is the copper loss of the motor, minus the copper loss of the generator, I a g square into R a g, is not? This is the total input power V I L. So, this is the only source of power. So, from this go on subtracting the losses. Set is running at some speed, there is I m, there is I a g, I f m, I f g. So, I subtract the copper loss of the field of the motor, copper loss of the field of the generator, this term, copper loss of the motor I m square R a m, copper loss of the generator I a g square R a g. And mind you, on the shaft of the machine I have not connected any mechanical load, I have not connected. Therefore, if I subtract all these losses, this must be equal to the rotational loss of both the machine. Of both the machine. Is not? Say it is equal to W naught, if you call it. Therefore, I will say rotational loss of each machine is equal to W naught by 2. So, I will continue with this in the next class.